Okay, in this second session, we're going to talk about how different aspects of the system, I guess it's the integration issue in terms of how models fit together, how different features of the system fit together. And the first speaker is someone I've actually known for a long time and worked with in several places. And he's always good for bringing up thought-provoking ideas. So, John Walton from University of Texas, El Paso, and John has maybe somewhat unique. He's been deeply involved in the Yucca Mountain project, and he's also been involved in engineered facilities for near-surface disposal.
All right, I'll go ahead and start. This is the, Roger said not to say anything about this. Is the title Roger made up for me when I was sea kayaking up in Alaska, so I don't know if I'm true to it or not here, but we'll just move on. The basic thesis I'm going to try to talk at you today is when you look at multiple systems in disposal facilities, and I'll just give you some examples today, sometimes interactions give you surprising results that you might not have expected or many people might not expect. And, you know, I'd like to see more of these insights you get from looking at multiple features incorporated in designs, and often they're not. Lower cost with better performance, everybody wants that. My view is that technology in the future will be great, but the low-hanging fruit is just better engineering design. It's here right now. We could do it with just thinking better about what we do. Often our designs are based on intuition, what people think is better but don't know, no calculations, and compartmentalized knowledge. The hydrologist do the cover, the metallurgist does another part, and they don't really talk very much. And these are some of the examples I'm going to show you. Again, I might have picked other ones, but these seem like they'd work. First thing I'm going to show you is a dissertation of Rob Rice. And what we did was a little parametric study with concrete vaults to look at to say, how does the shape of the vault affect the performance? Very simple study. So we did a parametric study. We put a below ground rectangular vault assumed. We modified the roof slope. Does slope make a difference or not? The size of the vault, and so on. And the soil covers layers around the vault. What difference does it make? The cover's modeled implicitly. That is, we have a leakage through the cover, and that's what the cover does. And we looked at the amount of water flowing through the vault, which is just a hydraulic performance anyway. This is the model domain. Don't want to go through it much, but the cover is just done by leakage rate, and we model half the vault and then scale it back up. The vaults could have clay or sand or loam around them. Loam is just kind of a generic backfill, and we did a bunch of simulations. We did basically hundreds of simulations. This just shows the gridding. You got to refine the grid around the edge to get it accurate. I don't think that's important here. Here's what I want to show you. Here's the results. And so we got like, I don't know, 100 simulations or so here. Infiltration, we mean by that is leakage through the cover. So here's how much water comes through the cover. Here's a really good cover. Here's a really darn leaky cover. Could get worse than that. Over here, seepage is the amount that goes through the vault itself. And this line right here is where if all the infiltration goes as seepage, so it's the one-to-one line really on a log-log scale, where all the water going through the cover goes through the vault. And a couple of things you can see here. One is here's different size vaults. So we go from a 2.5 meter wide vault, just a little bigger than this, to something bigger than the size of this room, the 40. And if we look over here, we find that the hydraulic performance is much better for small vaults than it is for big ones. There's a huge scale effect. And the scale effect is that small is better than large. And so that's pretty interesting. And the other thing we see, if we say we follow the 10 up, is if you follow it up for a while, what happens, they all reach this shelf up here where seepage through the vault is independent of the cover performance. Right? And just earlier, Craig Benson was saying, well, you take some brand new engineered covers, right, and you get leakage rates of 0.1 to 5 centimeters per year, and those are relatively new covers, not 100-year-old or 50-year-old covers. If you get older covers, it gets much worse. So what this graph would suggest is that if you have an engineered cover or you don't, it doesn't make a darn bit of difference to performance of these vaults because you're up here in this flat part of the curve where it's independent. Right? Unless that covers can be made better than what we're making them, they don't do any good. Here's another one. What we did is we started with what we called an intact vault that had low permeability. Then we had a second one where we put cracks in the vault and put an equivalent hydraulic conductivity and characteristic curve. We did the simulations. They look a little bit different, but we still see a shelf, not completely flat, but it's close, and we still see a scale effect. Right? Small is better than big. So you might ask why we get that. And the reason we get this behavior is perched water is probably the simplest explanation. As the vaults get big and as we get more water coming down, what happens is you get a little bit of perched water. Here, if you can't read it, dark green is more moisture, or dark green, blue is more moisture, light blue is less moisture, it's drier. And here we have one where we just change the size of the vaults and so the simulation. So here's a little vault, here's a 20-meter vault, and what you see is the little vault is still not perched. And so what happens is the water is diverting very efficiently around the little vault and not going through it. Whereas the big vaults, what happens is they start getting perched water. And if you think about it, once you get perched water on a vault, it means the hydraulic gradient through the vault is 1, right, or thereabout. And you got a unit gradient. And if you get another 10 centimeters of water on top of it, it's still about the same hydraulic gradient, so it doesn't change the flow rate much. So once you get perched water on top of a vault, the flow rate's pretty independent of infiltration. And that's why we get that funny shelf and the results we did. All right. So lateral diversion around a water around a, I say cover, but I should have said a vault, is scale dependent. It works better for small scales than it does for large scales. Water perches on top of large vaults even at low infiltration rates, and so that detects the performance. Once perched water forms, infiltration between the cover becomes unimportant. Smaller modular vaults are better. Okay? The other thing is that modular vaults also allow infiltration of mixing water. So I'm going to look at that a little bit. But first, let's look at this curve. The other one we looked at, this is just plotting the results a different way, and it's kind of hard to read. But here's one where we change the slope on the roof, 0 degrees, 10 degrees. Here we change the infiltration through the same range. And here's the seepage flux. And what you're going to get is this flat area up here, and this flat area is where you have perched water. So once you get perched water in the vault, it becomes pretty much independent, the seepage does, of anything else. And so that's kind of all I wanted you to see out of this funny diagram. So the percolation study, what are the conclusions out of that? If you put a clay layer or any sort of impermeable layer, it wouldn't have to be clay, adjacent to the concrete, lower water flow through the vault. It slows degradation because it slows the gas, CO2 and oxygen into the vault, and it enhances hydraulic performance. Smaller vaults are better, kind of counterintuitive. Roof slope, not very important. That kind of surprised us, thought it would be important. Most of the time, covers, engineered covers, are ineffective. That is, they cost a lot of money, they don't do anything for you. Right? Let's switch gears now. We're going to look at one of the dictums we see a lot, which is people say, you don't want to put a vault below the water table, that would be completely evil. Clearly, you get a lot more water going through the vault, it's just not a good thing to do. So what we did, I did this many years ago, so some of you have seen it before, is just test this little hypothesis that's widely held, and we do a little simulation, numerical simulation, where we take 2 vaults. You got the same vault, one's above the water table, has a cover over it, right? One's below the water table, and we look how much water goes through each vault and compare the two. So here's the results. What we did is we took, now I'm calling it net percolation through the cover because it was done at different times. So this is the leakage through the cover, all right? How much water in the unsaturated zone. And this is the ratio to the amount of water going through the unsaturated zone location versus the saturated zone location. And here's 3 different hydraulic connectivities. Here we've got a degraded vault right here, and these would be more intact, low permeability vaults right there. And the first thing you see is the ratio is greater than 1, not less than 1. And what that means is there's more water goes through the unsaturated vault than the one in the saturated zone. And again, the reason is perched water. What happens is perched water forms on these big vaults. Once perched water forms on a vault, you have a unit gradient. So in the unsaturated zone, you got a unit gradient of 1. In the saturated zone, typical gradients are 10 to minus 2, 10 to minus 3, 10 to minus 4. So just right off the bat, you've got about 1,000 times more water or so going through the vault in the unsaturated zone, as long as it's a relatively low permeability, large vault, which is what we tend to make. Okay? I mean, all these things depend on certain things. Also, a secondary effect is that in the unsaturated zone, you tend to expose the top of the vault to flow, so you have a bigger area, whereas when you're below the water table, it's the side of the vault. So that makes an effect too, but that's not the dominant effect. The dominant effect is the perched water. Now, you can argue other reasons you should put it in the unsaturated zone, easier to construct and so forth. I'm not saying you should switch, but some of these hydraulic behaviors are kind of surprising to people. This just shows the thing. You got perched water here, up here, unit gradient. You got a lower gradient down there. And so what do you know? More water goes through this one than that one. Let's switch to another thing now, and that our performance standards are based on peak dose. They're not based on release. Right? And so peak dose has to do with release, and it has to do with mixing. You can call it release rate divided by the mixing. And so both parts of this equation are important. The release rate's important, certainly we want to minimize that, but so is the mixing. Right? And my view is that peak dose should be managed by both. And you know, we should try to minimize spikes in release as well. So remember, Dave Esch had a slide where I didn't get to look at it in detail, but where he looked at and it said, you know, at this study, I don't know where that was, Dave, West Valley, where, you know, we got a rainfall event, and what do you know, more water came percolating through the vault. Well, we ought to be able to try to deal with that. So let's look at two different concepts. I'm sorry my graphics so poor, but I ran out of time, and I'm not too good with the software. But here's two different design options. One, the green's supposed to be the grass on top, and the black's supposed to be your engineered cover. All right? So in one case, we've got a classic system of vaults like E-area, or like the saltstone's going to be we saw this morning, where we've got this huge monolithic cover, okay? And it covers the whole site, and then you get a huge pyramid, you get so much runoff, you got to do an erosion barrier and everything else, and your costs go up. And you compare that to one where you just have modular features where impermeable layers go over the vault, and there's no classic cover. Well, in this one, all your mixing water goes way off here, causes erosion problems. Now, in the second one down below, the mixing water you put down below with French drains right near the vaults. And if you make these vaults small enough, and I'll get to that in a second, what will happen is this water will mix with the leachate before you get the compliance boundary, and all that mixing water will lower dose by a peak concentration and dose by a factor of 10 or 100 just right off the bat. Right. So this kind of says that smaller vaults with clay or at least some kind of impermeable thing against the vault are more reliable and lower release than the big covers. Now, I'm not going to derive this, but I put it in actually the appendix to this talk because I didn't want to spend time. But you can sit down and do a simple derivation. If the vault size is less than 10 times the distance to the compliance boundary, then what will happen is the water that goes beside the vault will mix with the leachate coming out of the vault before you reach the compliance boundary. And so that mixing will occur and lower your peak concentration. So that's one of the design parameters that ought to be in everything, in my view. If you put clay or other barriers over the vault itself, the vault lasts longer, as well as performs better hydraulically. If you combine plastic and brittle materials under high effective stress, what will happen is the effective stress means like the clay smashes into the cracks and they seal better than either one alone. And the modular design is also cheaper because these big covers cost a lot of money. I'm saying to get rid of the covers and just put layers over the top of the vaults, where you can do that anyway. Now, you can't always do that in the tank farms, but like the saltstone, you certainly could. All right? So I'll try to go some of this because I know it's repeating. But improved design, one way to improve design, there's a lot of other ones I haven't even thought of, I'm sure. Replace the monolithic landfill covers with modular designs. Okay? Conceptually, the cover should start at the top of the vault. Okay? Top of the vault, not the land surface, because that's a good, strong thing. That's where you want to start. And on top of the land, you just have backfill or natural. You put a building up there, for all I care. So all the layers goes close to the structure. You blanket the structure, not the site. Again, you have to get your scales right. Smaller vaults work better, and you have to get this distance, X over 10. Between the vaults, you put French drains to infiltrate the water that goes around them, and that mixes and lowers your concentration. You got less runoffs. You don't need erosion barriers and big rocks to stop the erosion anymore. Compatible with uses above, and you get 10 or 100 times reduction in peak concentration without even trying. All right? So this I've showed before. Just this should be replaced, except these should be smaller if I was a better artist. Okay. So now I'm going to hit on some other PA issues. There's some of the things here are paragraphs that I could have talked about, and I've done other places that I think are also interesting, and hopefully they'll stimulate discussion. Probabilistic analysis. We all like to do this peak of the mean now and do probabilistic. Well, we did a little study and we said, well, let's assume we have a little nominal disposal site that obeys simple equations. Right? Then we'll take the standard Monte Carlo method and we'll see if it reproduces the risk from this little imaginary site. And if the Monte Carlo method works well, it ought to reproduce an imaginary site, a nominal risk, pretty well. Turns out it doesn't. It tends to, if you use the peak of the mean, it systematically underestimates the risk from the nominal site. And so some of these tools we use have methodological problems that aren't really fully understood, that can fool with our risk. All right, I can fix that. And transients. Another big thing I think in PA is transients. And I think that in nature, most peaks come from transient events, and they don't come from scale up of steady states. And whereas PA, we scale up steady state. Often we say, and you see this at the Yucca Mountain PA and every PA I've ever seen, more seepage, more infiltration is always conservative. Overestimating the amount of water flow, and therefore I'm conservative. And the fact is that doesn't really follow. We saw the example of the tank with Karthik, and it turned out if the tank lasted longer, it was worse for the PA, a little counterintuitive, and that was talked about. But let me give you a simple example of a leaky dam. So I've got a big reservoir above my city, and let's say, I'll be conservative and assume the dam leaks really high. Well, if the dam leaks all the time, then the reservoir doesn't fill up. And if we have an earthquake, I don't have much of a flood. Whereas if that thing's perfect and doesn't leak at all, and I have an earthquake, I get a humongous flood. Well, we can see a lot of cases like that that might hit us in PA. You can see a lot of examples at Yucca Mountain. You can do one simple example is, let's say you have corrosion products, iron corrosion products. They have a big KD on the corrosion products. Well, what happens is the amorphous stuff turns to crystalline material, surface area declines with time, and perhaps all that stuff was absorbed early on is released. Storage and release. And there's a transient phenomena that could lead to a peak and release. Right? There are a lot of other ones. But I would argue that in PA, we need to focus on these transients and not just say scale up of steady state. We'll do it. Another thing I think I'd like to see, and this is just down the pike, is if we have all these vaults and all of a sudden the vault fails and we've got waste inside of it, have we really thought about when that roof fails, do we have any preferential flow pathways built into the waste in the vault so that water leaking in will go still around the waste in the vault if we have things stacked up inside there? And it seems like we might be able to think of some ways that it would. That's kind of, maybe it's a tertiary and just down the road. Other thing, and this is probably just my bias right here, maybe I'll stir up some controversy, is I think we should try to avoid the infallible barrier proof. Example would be Yucca Mountain. We have our alloy 22, and everything depends on the alloy 22. And so you have this big proof that alloy 22 won't corrode. And that may well be true that it won't localize corrode, but there'll always be skeptics out there that are hard to convince that it won't. And I think and you don't need to do that at Yucca Mountain, I would argue. And so I think we should avoid the infallible barriers. I just think it's a poor policy that leads to cost. All right, so anyway, that's basically it, is that traditional covers, in my view, are ideas that belong with landfills, not with DOE facilities. All they do is waste taxpayer dollars. Maybe it's good stimulus, I don't know. Better design is the low-hanging fruit. We can do better design even without new technology and save money. And I would like to see, PA analysts have seen a lot of time looking at poor designs, and what we do is try to tweak a poor design. And I'd rather see some money go into a bunch of PA analysts to say, how can we do brand new designs that work better from the start? Okay, so that's it.